This is Free Range Digital Design Foundation Modeling Chapter 23. This is the second lecture. What we're doing is developing the notion of finite state machines, otherwise known as FSMs, and we're doing it through a couple examples. And we've done 2 previous examples. This lecture we'll do a little bit of review and do 3 more examples. FSMs are general, mostly they're used for as controllers of other circuits. So it represents hardware control of hardware. So they're essentially very structurally simple in that they're 2 decoders and 1 register, and you've seen the register and decoder and 1 decoder in the last set of lectures, and now we're going to work towards having both decoders in here. And we are developing a kind of a mid-level intuitive feel for this. Lots of books start at low-level flip-flops and different types of flip-flops even, but we're going to keep it up at a high level. This is our general model of a digital circuit. What we have here is sequential circuits, combinatorial circuits, and maybe computer peripherals, maybe a model or maybe set hardware that we're going to interface with, and we're going to control it with something. In particular, in this course, we are controlling it with state machines. Often you can control it with microcontrollers, which are much more powerful, yet it's kind of a software solution, whereas state machines are a hardware solution. For our first example here, we have yet another counter. It's a 2-bit up counter, binary up counter, so we know it counts in 0, 1, 2, 3, very much like the previous example. But we have here is now a CE input. CE is an acronym for count enable. Oftentimes it's another acronym also, but count enable is what we're going to be interested in this time. So if the count enable is asserted, that means the circuit counts. If the count enable is not asserted, that means counter does not count. That means it holds its state. Transitions happening on the clock edge will only happen if the count enable is asserted. For this diagram, or for this problem, first thing you want to do is a state diagram. It's a 2-bit counter, which means there's 4 possible states. So let's go ahead and crank those out. Our starting point will be to generate a state diagram for this problem. You've seen most of this before. This is a little bit different, so let's crank this out. This is the basic state diagram. There's the 4 states, and I know it's going to count, so let's put the state transitions in there. This one is a little bit different because it counts conditionally, and for it to count, I must have that CE on, CE turned on or asserted. And so that brings up the issue of what happens when the CE is turned off. The CE is turned off, that means it holds state. That means it does not transition to the next state, which is the counting sequence. It goes back to the same state it's in. So we can put those in here. That is it for the state diagram. 4 states. I've got each state with a name. I've got the count indicated in each state. I've got the transitions associated with each state. Notice for every state there are 2 transition arrows leaving that state. So the next step here is to set up the underlying hardware. And for this problem, I think we are going to switch away from the flip-flops and we're just going to go to registers. Okay, so here we go. This is a 2-bit counter. There's my 2-bit register here. The next part of this circuit is I need to set the input to this register here to be the right thing such that it supports this requested operation of this counter. So what we're going to do is, once again, we're going to design a decoder on this, and that decoder is going to provide the next state information for this register. So let's do that. So when CE is not asserted, the count enable is turned off, so this thing holds state. And so what I have here is this is the state, and this is the next state. Okay, so when it's in 0, 0, the CE is turned off, it stays in 0, 0. And so this is true with all these inputs. Because the count enable is turned off, it doesn't count. What happens is it counts down here. So this is going to be 0, 0 goes to 0, 1. which we see in the time when the state diagram, 0, 1 goes to 1, 0, 1, 0 goes to 1, 1, and 1, 1 goes back to 0, 0. So this is our PS NS table. It's in something in tabular format, so that defines a decoder. This is going to be our decoder. We're going to call it NS. DCDR, which is next state decoder. Inputs to this decoder are the current state and the CE input. Pretty good. I think I'll try to clean it up a little bit and make it a little bit more readable. And I think that is once again done. Here's an example timing diagram for the circuit. Notice that when CE is turned off, the count doesn't change. Now, I put the little X in there, which is arbitrary. You don't really need to put that in there. It could just go straight on there without that because the output didn't change. But notice all changes are, in fact, when it does change, synchronized with that clock edge. You can see the changes here. These are holds, and we are done. Now this problem is, once again, it's similar. It's still a 2-bit counter, but now we have, it's an up-down counter, so it counts both up and down. So this up input is going to decide how it counts. So if up is asserted, it counts up. Up is not asserted, it counts down. Now this is a typical operation. I could have put an up input and a down input. Generally speaking, inputs are expensive, and we try to reuse inputs when we up. Asserted counts up, otherwise it counts down. First step is a state diagram. Let's do it. It is a 2-bit counter. I know I have 4 states. There are my 4 states. Now this is either going to count up or down. So here is, we'll put these count up arrows on there. It also may count down. So I'm going to put those count down transitions on there. And essentially what I need to do lastly on this is put the conditions associated with those transitions. So this is going to be up, this could be up, not. That is it for the state diagram. We'll just put it this. We need to do the hardware for this. It's a 2-bit counter. What I need here is to drop a decoder in there, which is the next state decoder. It's going to give me the new states to this thing. Actually, the other input to this next state decoder is going to be the up input. So this is a decoder with a 3-bit input and a 2-bit output, and so we could model that with a table, and let's do it. When up is not asserted, when up is 0, it's going to count down. So here's our counting down. 0 rolls under. It's circular in nature. We'll talk about that later. These counters naturally roll over and under without any effort. 1 goes down to 0, 2 goes down to 1, and 3 goes down to 2. This is the downs counting side, and here's the up counting side. This is something we've worked with. It rolls over automatically. So once I've defined this counter, this is the PS right here. Here's my next state. We might as well label the count plus in here just to be complete. I think we're going to call this one done. So notice once again, I haven't really said this, but there's no clock signal in the state diagram. There's no clock signal in the PS NS table. So we'll put that in there also. PS. You never see clocks written in the state diagram or in the PS/NS table. It's understood that the transitions are synchronized with the clock edge. Call this done. Here's an associated timing diagram. You can see that when up is turned off on that clock edge, it does in fact count down. Here's up is turned on, it counts up, and you can see that operation happen throughout this thing. Once again, everything, all the operations are synchronized with the clock edge. So this is our last example of this lecture, and this is also a counter, but it is a Stone Age unary counter. So the issue is it has a Stone Age unary count rather than a binary count, which is no big deal, but it does have an issue here. We're going to write this out. So the Stone Age unary is going to look like this. and it's going to be circular. So let's do the state diagram first. Once again, even though it's a 3-bit Stone Age binary up counter, there's only 4 possible values, and I'm going to represent those values with 2 flip-flops, or a 2-bit register in this case. So there's only 4 states in this one. There's a count enable on this, so let's go ahead and put that in. This is similar to another problem with the count enable. When the count enable is asserted, it does a typical counting, and when it's not asserted, it's going to stay in that given state. It counts when the count enable is asserted, otherwise it doesn't count. You know, this is the state diagram, of course, and as we step through this, there is an issue that you haven't seen yet, so we have to worry about 2 things this time. We have to worry about the next state decoder, and so let's worry about that now. Let's put a register in here. My next state decoder, it's going to take the present state and formulate the next state, but also have a CE input. Let's talk about this. Let's generate this table first. And so it's going to be CE and just call it ST. From this, we need to still fill this in. The ST is the state, so this is going to be ST, and we can make this. So there's the state. All we're worried about is the state on this one. So the state, if it's not asserted, the state does not change. Here we have the CE asserted, so it does change state. 0, 0 goes 0, 1. 1 goes 1, 0, 3, and 0. I've seen this before. Circular in nature. So this is going to be, this is a hold, and this is a up. The issue here is we haven't put this count in there, and so we need to put the count in there. Only way to do that is to drop another circuit on the front of this thing, and the output is going to be count. The issue is there's 4 states. The output does not depend on whether it's being held or not. The output only depends on the state. So for this coder here, all we need is to worry about the state. So we can put that in there. We can make a new table. Here's your state. There's the state. Here's the count. And the count is going to be 0, 0, 0, 0, 0, 1, 0, 1, 1, 1, 1, 1. So check it out. There's a table. Once we have a table, it naturally becomes a decoder, and once we have the decoder, we just call it a decoder. But this is a special decoder. We're going to give it a good name here, output DCDR. In reality, decoder takes in the present state and kicks out a count. So we're associating a count, the 3-bit Stone Age unary count, with the states. Now the way we assign these states is somewhat arbitrary. We could have assigned them some other way using 2 bits though, but we it's easy to keep them in like a binary count order. Nothing real special about that. But the important thing is that this counter is going to count in this sequence. This is what the outside world is going to see right here, even though the inside world is somewhat counting with a standard binary count. No one knows about that. That's the states. The output of this circuit is where the Stone Age unary count is, and that's all the outside world sees. So this is a classic circuit. This represents our 2 decoders, what we talked about before. We have both the next state decoder, which we've been working with several times, and then we have an output decoder. Of course, we also have the state registers also. So the issue here is I could have done this not using output decoder, but I would have needed a 3-bit register. And so the problem said, don't do it that way, use 2 bits. And because I can only use 2 bits for this counter, it's a 2-bit counter, I had to use an output decoder. So once again, we can see the count action here. The count is turned on, so it counts up, and we can see it count is turned off. So this is a hold, typical counter. Once again, this is what the outside world sees. It doesn't see the actual state variables or the output of the register, the underlying register in this problem. That's very typical. The output for all the previous problems, the output of our circuit was the output of the state registers. For this problem, the output of the circuit was not the output of the state registers. We had to drop an output decoder in between those to essentially massage the output into something that we wanted.